Thank you for the introduction and the invitation. I'm very happy to speak here, especially in honor of Dustin's professor position. I learned a lot of mathematics from Dustin over the last years. And I try to choose a topic for today which is kind of connected to Dustin's mathematics in some way. And so this is based on joint work with Johannes Anschütz, Juan Esteban Rodriguez Camargo, and Peter Scholze. But I should warn you that this is very much in progress. So yeah, there are still lots of things that we need to figure out. So I'll try to explain at least some constructions and give some motivation for this construction. So before going into what we do, I'd like to start to set the stage by maybe some kind of brief and informal recollection on the theory of diamonds and V-stacks. Which is due to Scholze. So as a motivation, for example, let's say we start with some nice finite type adic space, so rigid space over a p-adic field like Qp. For example, the analytification of some scheme over Qp. And let's say we care about understanding étale cohomology of X with Fp coefficients for the same P as the P of the base field. And to do that, we can try to use some kind of Artin-Schreier sequence and try to study the Frobenius fixed points on some sheaf which looks more like a coherent sheaf, which is so on X you have the integral structure sheaf of functions bounded by 1. And you can reduce this mod P and try to rather analyze first the cohomology of such a sheaf. But then the issue you run into when you try to study this is that this sheaf is not acyclic locally for the étale topology. I mean, to kill the higher cohomology, even like on affinoid pieces of such a sheaf, you need to use a finer topology, which is a pro-étale topology. And then you actually get the desired vanishing because you can. Okay, so you can you have a basis for this topology, which is given by affinoid perfectoid spaces, which are not adic spaces of finite type anymore. These are adic spaces on which you can somehow extract a lot of piece power roots of elements. And for this basis, you have some, at least in this almost sense of faultings, you have some vanishing for cohomology. And then, for example, if you try to prove, if your rigid space is assumed to be smooth and proper, and you try to prove some finiteness results for this cohomology, you can do it for this one, and then try to mimic this Cartan-Serre argument for finiteness, like working locally, using this pro-étale topology. And so you see that somehow for this problem, you are led to, instead maybe of working directly with this rigid space, you kind of want to replace it by the collection of all, say, affinoid perfectoid spaces mapping to X, and in some kind of coherent way. And so, I mean, by descent theory, we know how to phrase this in a precise way, and this leads to the notion of a diamond. So, because perfectoid spaces, you have a tilting going from perfectoid spaces in any characteristic to to perfectoid spaces in characteristic P. You can actually restrict to consider perfectoid spaces in characteristic P. And then a diamond is defined to be a sheaf for this finer topology, this pro-étale topology, on this category that you can present as a quotient of some perfectoid space by some pro-étale equivalence relation. So this definition is kind of analogous to the usual notion of algebraic spaces, but in this pro-étale world. So you have replaced schemes by perfectoid spaces, and you have replaced the étale topology by the pro-étale topology. And well, typically for a rigid space as above, you can, let's for example assume that for simplicity that X is smooth, and then you find a pro-étale cover, pro-étale Galois cover, with Galois group G, a certain pro-finite group, and then the diamond associated to X, which is written X diamond, will be defined, presented as the quotient of, well, the sheaf represented by the corresponding perfectoid space in characteristic P, which is a tilt of X tilde, by the action of G.
So you do it on a affinoid, for example, or to get the Galois cover of X. It's locally for affinoid.
Right, yeah, let's say affinoid. Yeah. And smooth is not actually a necessary assumption. In the smooth case, it's easier to produce such a cover. Okay, this a priori maybe looks like it depends on the presentation I chose, but you can actually write down a functor of points description of what this diamond is associated to a rigid space. So as a functor on perfectoid spaces, X diamond sends S to untilt S sharp of S. So an untilt is another perfectoid space, not necessarily in characteristic P, together with an isomorphism between the tilt of S sharp and S, plus a map from S sharp to X. Okay, so that's the basic idea of diamonds. And maybe let me make at this point 2 further remarks. So I gave as a motivation the study of, say, FP cohomology, but say, what about if you now care about QP cohomology? Of a rigid space. Then, of course, the use of the pro-étale topology is even more natural, because Batch also have shown that the usual slightly ad hoc definition of étale cohomology with QP coefficients can be really naturally seen as pro-étale cohomology of the pro-étale sheaf associated to QP. So it's really directly sheaf cohomology in this case. And well, in this situation, you could first study ZP cohomology and then reduce mode P to reduce yourself to this situation. But since you work with a poetal topology, you may as well want to understand cohomology of poetal QP local systems on such a rigid space X, and then you don't necessarily have a stable lattice, and you can't really reduce to this situation. So maybe you'd like to find a different way to do it, and the issue a priori is that on the diamond you have a natural structure sheaf which lives in characteristic P, because this is a functor on characteristic P perfectoid spaces. That's not what you care about if you want QP coefficients. Of course, X diamond, this construction is functorial in X, so it have a map to SPA QP diamond, which is parametrizing untilts. And so you have also a natural structure sheaf living in characteristic 0 on the diamond, but this one has no Frobenius anymore. So you can't really use any kind of Artin-Schreier argument there. So the trick is to somehow lift everything to Witt vectors to be able to handle QP cohomology as well. And then you are led to considering another diamond associated to this situation, which I'll denote Y X diamond. So maybe a standard notation in the field is to write it Y0 infinity X diamond. So that's really defined as a diamond. And this is defined by descent from the perfectoid case. So in the perfectoid case, if S is perfectoid, then this is literally defined. I mean, there is actually an actual adic space, which is, so what you do is you take the adic spectrum of Witt vectors. So let me write S as SPA RR plus. You take the adic spectrums of WR plus, and you want to remove the locus where, so this has, you can fix some pseudo-uniformizer or topologically nilpotent unit in R. And you want to remove the locus where either P vanishes or Dirichlet of this pseudo-uniformizer. So it's a non-affinoid adic space, some kind of Stein space. But yeah, in general, you only define it by descent. And of course, the idea is now that you have a Frobenius on the Witt vectors with P inverted, and the Frobenius invariance will be given by QP. So you can rewrite QP cohomology of X as the cohomology of the structure sheaf on this diamond. On this diamond modulo the Frobenius action.
So S is perfectoid of not necessarily characteristic P, is of characteristic.
Well, to write down this formula, I assume that S is perfectoid of characteristic P. Yeah. And there is a very nice formula proved by Scholze for this, what these diamonds look like. Maybe I call this diamond formula. Is that this YX diamond is in fact a very simple product. It's the product of X diamond as sheaves on perfectoid spaces in characteristic P with a diamond associated to QP. Oopsie. And this follows from some adjunction between Witt vectors and tilting. So I come back to the formula later in the talk. Okay, so that was my first remark. The second one is that, of course, when you start doing this, it's not really necessary to restrict to diamonds, or in other words, to some kind of algebraic spaces in this setup. So diamonds are by definition poetal sheaves, there are even sheaves for a finer topology also introduced by Scholze, which is called the V topology. And instead of looking at some kind of algebraic spaces, you can pass to stacks. And so you can also look at stacks for the V topology on this category of perfectoid spaces in characteristic P, which are called V stacks. And for example, this allows you to consider objects like the following one. So let's say you have G, which is a locally profinite group. And then you can look at the classifying stack. So point just denotes the final object of the topos of sheaves on perf, sometimes also denoted by p-adic FP, which is a classifying stack like this, parametrizing G torsors. So this is the notation for so any such topological group. One can naturally associate to it by looking at continuous functions a certain proétal sheaf on perf. And this is useful to study in a geometric way continuous representation theory of the topological group G. As an example, so this, for example, plays an important role in the work of Scholze, where this naturally arises in the following way. If you take G to be like this kind of fancy G to be a reductive group over QP, and you define the corresponding locally profinite group to be the group of QP points of fancy G. Then if you consider so before I introduced this construction Y X diamond, and if you consider the functor, the stack, the pre-stack, sending S perfectoid space in characteristic P to the groupoid of G bundles on Farag-Fontaine S, which is by definition the quotient of this adic space YS by the Frobenius action. Then this is actually another example of V stack, which contains as an open substack. So let me denote it by bun G. And bun G contains as an open substack this classifying stack. So you can even promote representation theory of G to the study of sheaves on this bunch. Okay, so in other words, like this framework of diamonds on V stacks gives you like a very flexible framework in which you can perform many constructions. And I mean, maybe this looks a bit artificial if you only care about rigid spaces, but when you start studying p-adic Hodge theory of rigid spaces, you may end up looking at objects like Banach-Kolmé spaces, for example, that I did not discuss, which are like really only just diamonds. They don't come from some honest adic spaces. Okay, so that's the nice feature of this theory, but this also has some drawbacks somehow. So this formalism is also not enough for some purposes. And I'll try to give two examples to explain why we need to go beyond this formulation. So one motivation comes from the study of non-abelian p-adic Hodge theory. So as said, if you care, so in some sense, this diamond associated to your rigid space remembers all kind of topological information about X, in particular the étal side. So if you study local systems, for example, you can just try to walk on the diamond, on the corresponding diamond. And more generally, you can consider the category of vector bundles. So X is, again, say a rigid space, and let me assume it to be smooth, over QP, or could also live over a complete algebraically closed field like CP. And you can consider vector bundles on the diamond, so by which I mean like vector bundles on X for the V topology. So these are like objects which, like O modules which are finite locally free, locally not for the analytic or the étal topology, but for this much finer topology. And they have some, I mean, these objects are relevant to the study of non-abelian p-adic Hodge theory, because these are actually some incarnation of what Faltings call generalized representations. And you want to understand this category, but and relate it to more analytic objects. This is a little bit vague, but I don't want to go into too many details here. Let me just say that on perfectoid spaces, this notion is the same as the usual notion of vector bundles by result of Kedlai-Liu. So you can certainly describe such objects by saying that you find a perfectoid cover, as we did before, and then you have to write some descent datum. But already in the case of a p-adic field, this is kind of inexplicit. Like, I mean, this is a category which is not so easy to understand. Like for a p-adic field like QP, you end up considering the category of CP semi-linear Galois representations. If you cover SPA QP by SPA CP and write the descent datum that you get. And maybe you want to understand this in terms of objects like in usual non-abelian Hodge theory over C, objects like Higgs bundle. And ideally, so you can think to vector bundles as like O modules on, like vector bundles on the diamond associated to X. And maybe you would like to have another geometric object such that vector bundles on this geometric object correspond to Higgs bundle. And you may try to understand the relation between categories of Higgs bundles and this category of V vector bundles by some geometric argument by relating these two geometric objects directly. The issue is that in these examples, and we could also consider the case of D modules as well, the issue is the same in both cases, that these are naturally like modules over the analytic cotangent bundle of X, which are like finite over X. And the ring of functions on this, like locally this looks like affine space over X, like analytic affine space. And ring of functions on analytic affine space it's kind of the continuous dual to the ring of overconvergent function around the origin. So the ring of germs of functions around 0 in the dual affine space. So if you imagine that you have some kind of Cartier duality working in this setup, you are naturally led to, you would like to define something like, for simplicity, for example, let's assume that X is just the affine line over your base field, the analytic affine line, of course. And then this means that the stack, which sees such that vector bundles on this stack would correspond to Higgs bundle, it should be something like the quotient of this analytic affine line by something which I will denote GA dagger, which is corresponding to the ring. It's co-represented by this ring of germs of functions around 0, which is something you may write K curly brackets dagger, and is by definition will be the co-limit of Tate algebra over n. So like this is corresponding to the functions on the affinoid ball around 0 of radius 1 over p to the n, and you lay this radius shrink to 0. But the issue is, so and the action here is the trivial action. So it's just relative classifying stack. And so it's natural to guess that Higgs bundles correspond to vector bundles on this. And more generally, for any smooth rigid space X, you could take the quotient of X for the trivial action by the over-convergent completion of the tangent bundle along the 0 section. But the issue is that this does not really make sense in the work of adic spaces. This kind of objects. In Huber's because when you take the adic spectrum of some Huber ring, it only sees it, like it does not see the difference between the ring you consider and its completion. But here, like here the pseudo-uniformizer is assumed to be P always. If you take the p-adic completion of this, you would just get the base field itself. So you don't see anything interesting. So it's hard to capture this kind of information in the world of diamonds and V-stacks.
So for the action, you're not using the embedding of
no, that would be corresponding to considering D modules. Yeah. Yes. Okay.
Sorry, I'm a bit lost. I mean, what do you mean by dual? I didn't get it. Dual. This ring of functions dual to germs at 0.
I mean that if you imagine trying to argue by Cartier duality, you would have to have some Hopf algebra and you try to compute the dual.
Okay, it's like a linear dual.
Yeah, okay. Continuous linear dual. Okay, it's just some kind of heuristic for why.
But the Higgs bundle you consider the purely algebraic. There is a notion in algebraic geometry of Higgs bundle, and then there is no analytic thing about like E going to E tensor of omega. I mean, the notion. So,
yeah,
so the Higgs bundle is like a vector bundle with a map to E tensor.
It's a Higgs field, yeah.
Yes, and this. So where is the convergence coming here?
It's because you are not using the sheaf of algebraic differential forms, but the sheaf of analytic.
Okay.
Right? So if you were working in the usual algebraic setting, I guess what shows up more naturally is the formal completion in this characteristic 0 case of GA. But here you get the dagger version because you are doing analytic instead of algebraic differential forms. It's like considering it's not the algebraic affine line, but it's more the analytic affine line. The ring of functions on this is like this inverse limit of ring of functions on Tate algebras. So when you dualize, you get something like this over-convergent space of functions.
So explicitly, does this mean the Taylor expansion formula for the Higgs field satisfies some convergence property?
Say again, sorry.
I mean, this analytic dualism, do you mean explicitly the Taylor expansion of the theta formula?
Well, you don't really see it on the category of Higgs bundles. Because any point of the algebraic affine line is already containing the analytic affine line, so you can't actually probe the difference just on the category of Higgs modules.
Okay, so there is no convergence condition because everything is convergent. I mean, okay. But now you're speaking in your sense.
I mean, maybe you don't only care about, okay, maybe I should also have said this. I think it's related to Peter's comment. You don't care just about V-vector bundles, but maybe you also care about some kind of quasi-coherent shifts with no finiteness assumption. I think for this is... okay, so the other motivation was coming from representation theory of p-adic groups. And the issue is very similar. It's back to my example of this classifying stack. So as I said, using this classifying stack, you can study like continuous representations of G. But it happens that this group G is not merely a locally profined group, but G, for example, could be a p-adically group. Like, for example, the QP points of a reductive group over QP. And then maybe you care about other kinds of representations of G, like locally analytic representations. If G has this extra structure. But this geometric object somehow does not really remember this information you have on G. And if you rather want to pass from continuous representations to locally analytic representations, it's like passing, as the name suggests, from continuous functions to locally analytic functions. But the space of locally analytic functions on this p-adically group G inside all continuous functions, it's a dense subspace. So you'd like to replace G underline, which is a spar of continuous functions on G over K, if K is my fixed, let's assume that everything is over some base perfectoid field K. You would like to replace this by something like, would denote like G locally analytic, which is something like the spar of, now you take locally analytic functions which can locally be expanded in power series expansions. But again, you run into the same problem as before, which is that, I mean, this is a dense subspace in here, and like you can't really, using adic spectra, you can't really tell the difference between these two. Okay, so that's somehow two motivations for trying to LA, like locally analytic. This is, say, if G is also, say, compact. And in fact, these two motivations are closely related to each other because of geometric sense theory as developed by Berger-Colmez, Pan, and Rodriguez Camargo, and so it's kind of the same problem, like two different instances of the same questions. And you see that the issue is not really about the fact that the formalism of diamonds on V stacks takes as an input perfectoid rings instead of maybe more general Huber rings. Because anyway, for the Poetal topology, which is the topology we use for the Schiff condition, everything is locally perfectoid. It's more about the fact that in this formalism, the test objects are always assumed to be complete in some sense. So you need to allow a class of test objects which are more general than usual, maybe complete Huber pairs. And this is precisely what the analytic geometry of Clausen and Scholze allows us to do. So this is what I want to explain next. And I mean, of course, not in full generality, but at least just briefly what, in the case we care about, which is this non-Archimedean setup. So this is a geometric framework in which you can speak about objects such as this GA dagger and this GLA for G p-adic Lie group in a meaningful and useful way. So the basic building blocks for the theory are so in the same way as you can define stacks like usual in algebraic geometry. You define stacks by first, say, defining affine schemes as opposite of the category of commutative rings, and then taking sheaves for some appropriate topology like Zariski et al. Or FPQC. In the same way here, basic idea is to, we replace analytic rings by a much bigger category of some kind of topological ring. And the rough intuition behind this notion is that an analytic ring R is a pair formed by the datum of some kind of topological ring, R triangle, plus a certain, so to this you can naturally associate the category, derived category of R triangle modules, and you want to single out a certain full subcategory denoted by dr inside dr triangle, to which you want to think as some subcategory of complete R modules. And of course, like this, it's not an arbitrary subcategory. It has to satisfy certain properties, but it's kind of stable under many operations, so it's very flexible. And then you define an analytic stack to be a sheaf. I mean, you could consider sheaves of sets or groupoids, but you can work directly in full generality and work with sheaves of infinity groupoids on the category of, well, what you may want to call affine analytic stacks, which is just the opposite category of this category of analytic rings. For a certain topology, which Clausen-Scholze called the Schrick descent topology. And of course, I don't want to get here into the precise definition of this topology, but it's in some sense, well, what we care about is one nice consequence of this is that for any analytic stack, more or less by definition of this topology, you get a category of quasi-coherent sheaves on this. which I will denote by dx, with a six-functor formalism. In such a way that if X is spec R, so the analytic stack, affine analytic stack associated to some analytic ring R, dx is given by dr. So you glue for some topology which, so in the affine case, you want to declare this category to be your category of quasi-coherent sheaves on spec R, and then you consider sheaves for a topology which allow you to glue, to descend these categories together with 6 operations. Okay, so that's the general, very general framework. So here we are in the more restricted setting of p-adic geometry, and so we don't really need to this full generality. Let me recall, classically, in p-adic geometry, you have the category of complete Huber pairs. Which contains the subcategory of complete Tate Huber pairs. And this in turn contains the subcategory of affinoid perfectoid pairs. And our diamonds were defined as functors on this smaller category. So this is a certain kind of non-Archimedean topological rings. Here you put the condition Tate means that you have a pseudo-uniformizer. And affinoid perfectoid, you further require that you can extract a lot of piece powers. And we'd like, as I said just before, we'd like a class of geometric objects for which you can detect things like GLA or GA dagger. And so you want, in the world of analytic stacks, you want to enlarge a little bit this category to be able to do this. But maybe the right way to do it is to do it in steps and explain first how to generalize this category and then this one and then finally this one.
Sorry, maybe a bit confused. So now you're talking about affinoid perfector spaces, but it's not necessarily characteristic P.
That's right. Yeah. Here I'm taking any characteristic. Okay. So I think I will have to be brief. So maybe the first thing I should say is that this is a Huber pair is a pair formed by a certain topological ring and some open integrally closed subring of power-bounded elements. And to this you can naturally associate some analytic ring with the property that the underlying topological ring is just the one given by A, and this category dr is somewhat determined by the choice of A plus. So for general analytic rings, leaving over the solid base, this solid, you can also somehow single out a condition which looks like this one, which tells you that you may want not to consider some arbitrary analytic ring structures on some topological ring over Z, but you may want that it's somehow induced by the choice of some subring of power of integral elements, and that leads to the notion of solid analytic rings. And then inside that, you want now to single out a condition which looks like this idea that you have a pseudo-uniformizer. If you have a pseudo-uniformizer in your Tate Huber pair, it actually automatically implies that the ring A is, so call this pseudo-uniformizer pi. A will just be given by you take some ring of definition, which exists by definition of a Huber ring, and up to changing A0, you can assume that pi belongs to A0, and you endow, then A0 is endowed with a p-adic topology, and A is just obtained by inverting pi. And here you want an analog of this in this extended framework of analytic rings. And this is a notion that has been singled out and studied by Juan Esteban Rodriguez Camargo. And this is a notion of solid bounded analytic rings. And bounded is a way to encode the idea that you consider some analytic rings on which any function is bounded. So in geometric terms, you look at rings such that any map from the analytic spectrum of R to the algebraic affine line will automatically factor through the analytic affine line. So for this to make sense, you need to assume that your analytic ring is living over Z double bracket pi. A map from this to your ring is like picking a pseudo-uniformizer. And then you impose this further condition of being bounded. Why I want to mention this world, so as I said, it has been studied by Rodriguez Camargo, is because for any such ring you can make sense of a dagger, it's dagger nil radical. And this is an ideal. In R. And the idea is that this is so there is an adjective dagger. It does not literally mean that you consider nilpotent elements, but rather you want to consider elements R in R, which are at least the underlying condensed group is given by the elements R in R, which are divisible by all powers of the pseudo-uniformizer. This is denoted by nil dagger R. And this happens to be...
It's an ideal in the abstract ring. When you use condensed formalism, it's an ideal in the condensed ring or ideal in the underlying ring, R star?
In the condensed ring here.
But to get it as a condensed ring, this is actually one of the main innovations of Rodriguez Camargo, to be able to define this as a condensed ideal.
Yeah.
Non-trivial to do it.
And I mean, the point of bounded condition is that it ensures that this is actually an ideal, roughly speaking, because the product of a bounded function by something which is over-convergently nilpotent in this sense remains over-convergently nilpotent.
Sorry, so to clarify, here you by rings you mean not like animated rings that just concentrate degree or something. Solid analytic rings.
In which case, sorry?
Solid analytic rings.
I think everything should be taken in the animated sense.
But here is a complication because somehow you say that the double parent pi because this solid to max to R it might be a part of data. I mean somehow when you say something, at least a priori this is part of data, and it's not clear to me why this could be a full subcategory or something.
Oh yeah, sorry, maybe that's okay. Yeah, sorry, I take it back. Yeah, sorry, I'm not being very precise because I'm not managing my time very well. But yeah, you assume that. Sorry, I did not mean that there is such a containment. By definition, a bounded analytic ring will come with a map from ZP solid, Z double parenthesis pi. Okay, so I was...
So what is it for usual Tate-Huber pairs, Tate-Huber ring?
For usual complete ones, I think this will just reduce to the nilpotent element. Nilpotent element.
Pi to the n divides r. No, but if r is like UP, and pi is p, then it always divides. What does it mean divides? It always divides.
Maybe I did not phrase it. Sorry, maybe.
You didn't say.
Divide somehow in. Once it shows a ring of definition or something.
Maybe I want to say that it belongs to the power bounded element. I mean, this is defined. R over pi to the n belongs to. Sorry. Yeah.
To r plus as defined for.
You can define the r plus and the r0 for any.
But this ideal is ideal of pi 0, right? Or some Smith ideal. I'm confused how.
Like all high homotopy groups will be in the.
They will be contained automatically in this diagonal radical. Like the typical example I have in mind is like this element T on this ring upstairs. Like this is an example of a diagonal potent element. Okay, and so once you have this notion of a diagonal radical, you can try to enlarge slightly this category of perfectoid test objects by considering the following notion. So you say that a bounded solid ring R is okay, we temporarily call them nil perfectoid. Maybe there is a better choice of terminology. If so, you can define the Dagger reduction to be the quotient of R by this diagonal radical as a condensed ring together with the induced analytic structure from R. And you want this to be corresponding to be the analytic ring associated to a perfectoid affinoid pair. So I will just write is perfectoid. So these are analytic rings over the solid which differ from over Z double parenthesis pi solid, which differ from perfectoid rings by some kind of Dagger nilpotent part. So they subject onto something perfectoid, and the kernel is Dagger nilpotent. And so then the game is to try to extend some of the definitions I explained before for this bigger test category. And so since I have only 5 minutes left, I have to be very brief. So the thing I wanted to start from is this diamond formula. So recall that X is an adic space over QP. Then I mentioned this diamond formula of Scholze. So these are defined as functors on perfectoid spaces in characteristic P. And I claim that, in fact, both sides will have a natural extension to functors on nil perfectoid rings over QP. So, okay, a priori, a diamond is a sheaf on perfectoid spaces in characteristic P, but in this case, I mean, both sides have a natural map to p-adic QP, so you can also just see them as functors on perfectoid spaces in over QP, and then you may try to extend them to this bigger class of test objects. And the funny thing is that some of the two extensions will actually be different in this case. So let me start by saying something about the left-hand side. So here we kind of just mimic in both cases we actually just mimic the usual definition. So recall that if X was affinoid perfectoid, this was defined as the adic spectra of W R flat plus minus the locus where P and Teichmüller of pi vanishes.
You mean the product? P times, okay.
Huh?
It's P of the product, yes?
Yeah, it's a product, yeah. Yeah, and this you could also rewrite as the inverse limit over Frobenius of the Witt vectors of, I mean, here you take plus or 0, it does not, you can also take all power bounded elements. This you can also rewrite as Witt vectors of the power bounded elements in R itself, and you take the limit under Frobenius. And so this suggests what you may want to do in general. So for no R, which is nil perfectoid over QP, you will do a similar construction. So you consider the analytic ring, which is given by so you can, in particular, any such R is, for any such, yeah, so Rodriguez Camargo has defined this subspace of power bounded element as a condensed subring, so you can make sense of this, and you take Witt vectors on the inverse limit and invert Teichmüller of pi. Recall that R by definition receives a map from the double parenthesis pi. And so you see this as a condensed ring, and you endow this with some analytic ring structure coming from R plus. And then you can consider okay, so whenever I say analytic stack, no, I will actually cheat and mean this in the sense of, no, we want all our functors or our stacks to be defined on this category of nil perfectoid rings, let's say over QP. And so now you take the functor which is co-represented by this analytic ring on this category, and this is what you may call is defined to be what I want to call Ys. If S is, or maybe X, if X is the analytic spectrum of R.
Sorry, so when R is over maybe Z for QP, so phi is defined just taking P's power? Yeah, just so which means?
It's the Frobenius on the Witt vectors.
So you take
so you don't need to take like
active
field or something. Just
what is R? You take for the
So R0 is a subring of power bounded elements. And you use the Frobenius on the Witt vectors. Maybe it's...
So the Frobenius is not an isomorphism anymore?
No. No, it's not. Yeah.
Does it stabilize it after some step?
No, it's really taking some kind of perfection. Like, as I said, if you do it for some, if R is really literally perfectoid, then it produces Witt vectors of the tilt. Okay, so let me just finish in one sentence by saying briefly something about the right-hand side. So what does the right-hand side on this diamond formula parameterize? It's like parameterizing some untilt. Where am I? Yeah. And maybe just one word about this left-hand side to come back to the original motivation is that I mentioned this spongy construction of Fark-Scholze, and no, I mean, the key point underlying the fact that you see this open substack, this classifying stack as an open substack of their Bungie, is the fact that this functor sending S to global sections of the structure sheaf on Fark-Fontaine S is given by the sheaf QP underline. In this new setting, if you do a similar construction with this new Fark-Fontaine curve, which would be the quotient of that guy by its Frobenius, what you get instead is actually QPLA. So that makes, so you see this locally analytic incarnation of QP. And for the right-hand side, I don't really have time to say anything, but just say that in the diamond framework, what this parameterizes is the choice of some. You start from a perfectoid ring over QP. This is a map to p-adic QP. And then you have to pick some untilt, some other untilt of the tilt of this perfectoid ring together with a map to X. And this you can think of as parameterizing degree 1 Cartier divisor on this space of Witt vectors of the tilt. And so here, similarly, you just mimic this again, and you define this this other side, which we call X prism, as some kind of moduli of, let me be very vague, on, well, on, like it's sending R to the moduli of degree 1 Cartier divisor on Y of unspec R plus a map from this divisor, let's call it Z, plus a map from Z to X. And in particular, inside this stack, you can define some substack, which now is, by analogy with the Batlury theory, is called the Hodge state stack. And this now really has the desired shape that I mentioned as the first motivation. So this is a gerb. It's not literally the classifying stack, but this is a gerb for the over-convergent completion of the tangent bundle over X, which was one of our motivations for extending these definitions. Okay, sorry, I'm sorry for going over time.
Thank you, Arthur. Are there any questions?
Maybe just to be sure, the overconvergence at the end, is it related to some smallness condition on the Higgs field, or it's nothing?
No, I think it puts no condition on the Higgs field. Yeah, but it's not a classifying stack, so it's not like you don't, if you take vector bundles or perfect complexes on this stack, you don't really see Higgs bundles literally, some kind of twisted form of Higgs bundles. This stack, like there is also some integral version that I did not have any time to mention, which is due to Batlury, where it's when you start rather from some kind of smooth formal model, and then there are many situations where it actually splits. For example, in the affine case, but I think this one that we get there is almost never split. So you don't just even if you know that this category of, say, perfect complexes on this stack identifies with the category of perfect complexes for the V topology on X, this does not tell you that Higgs bundles are the same as V bundles, I mean, which is not true in general. For p-adic fields, for example, it's not true. So yeah. Yeah, Ben Hoyer has some results in the a geometric case where X is assumed to live over, say, CP and is smooth, but also assumed to be proper. But I don't think this just like follows from.
You can recover the result of.
No, that's what I was about to say. Well, I don't think you can really just recover formally from this what he does. No, it's not even if you reformulate it, he's not really proving that this stack splits in this case. That's not correct. So you need more work to recover his results.
So do you have anything to talk about? I mean the coherent cohomology of this stack and how to compare with the usual cohomology theory, for example.
Yeah, that's a good question. I don't really know. So yeah, as you notice, the notation suggests that it's inspired by Batlluri's definitions, and it may have some relation with prismatic cohomology. It could be related to, so you have your, say, smooth rigid space, and you pick a formal model, and you can consider its prismatic cohomology, but somehow localized. Let's say everything lives over CP, so prismatic cohomology gives you some A-inf modules, and you want to localize away from the vanishing locus of Teichmüller of a pseudo-uniformizer, and then take some perfection of this. So this cohomology of the structure sheaf on this stack could be related to this, but I'm not really sure. Actually. Yeah.
I was wondering, because you had these two sides and you said both generalized to your world, and I assumed you were going to say something about the relationship between the two generalizations.
Well, they are related in this sense, I guess, that one is parametrizing divisors and on the other. I think in the Fark-Scholze setup, like these two diamonds are the same, but there are like two different Frobenius that you can consider. And if you divide by one, you get somehow by the Frobenius of X, you get the Fark-Fontaine curve associated to X. If you divide by the Frobenius of QP, you get something called div1, which is parametrizing divisors on the Fark-Fontaine curve. Here on both, you have just one Frobenius, but yeah, in some sense, the quotient by Frobenius of this guy is, I imagine this as some kind of analog of div1 in this setting.
So in your setup, you don't have a map between the two sides, or do you?
No, I don't think so. But, well, if you have a functor on nil perfectoid rings, you can always restrict it to, maybe also I should have, yeah, if you restrict to perfectoid rings, you can always restrict to perfectoid rings. And this is an extension in the sense that the construction I'm describing, if you restrict them to perfectoid rings, you just recover this.
Okay, but you generally don't have.
I would also like to request one example of a nil perfectoid ring that is not perfectoid.
That guy over there, I think. Well, the reduced quotient is trivial.
So we take K to be perfectoid, and and then we have just the string of germs of functions in the neighborhood. Yeah. Okay.
I think more generally you may try to look at, take some quotient of a perfectoid ring by some finitely generated ideal where all elements have infinitely many p-spiral roots, and somehow take the co-limit perfection, but without completion. Okay. I would guess that this should be dagger perfectoid as well. Sorry, nil perfectoid.
Is it possible to do tilting for this nil perfectoid things?
Well, you can always take the and that naturally shows up when you try to describe the fibers of this object over some fixed base. You can, but I did not. You can always just take the dagger reduction and then tilt it. Yes. But you can't really go from characteristic P to characteristic 0. Yeah, even over a fixed perfectoid base.
So being maybe quite naive. I mean, your theory is in mixed characteristics, but is there any reasonable theory for equal characteristics, or it's just very simple in equal characteristics?
I did not. Yeah, I understand the question. I did not really think about it. I would imagine you can also do something in this case.
Over breakfast model? I mean, like if you start with an Adic space over FP, then you can still do this YX diamond kind of thing.
But I thought that the question was more about like equicharacteristic local field.
I don't know what's the exact question.
Yeah. I'm not sure. Did you mean you want to replace QP by? Yeah. You can somehow replace QP by FP and do some constructions there. But if you were asking about replacing QP by, say, something like Laurent series over FP, yes. I guess it should be possible to do something. I just didn't.
No, I just wonder whether if we do such a replacement, then the whole theory is trivial or something.
No, I don't think so. I don't think so. But like, I mean, this theory also. In the diamond V-stack setting, you can replace QP by some equicharacteristic local field, and that's still an interesting.
I mean, equicharacteristic. I mean, somehow, just like here, there's a complication. Just like in algebra case, you consider double cut, which is much more complicated than a crystalline. I mean,
okay. So then you mean something different from what I. Okay, yeah. I think if you replace QP by FP, you can basically like this prismatization construction becomes something much more simple. Yeah, you don't need anything like Witt vectors. But I think it's still an interesting construction.
Well, so locally analytic representation theory over equal characteristic local fields is maybe a bit funny.
Yeah, this I don't. Yeah, okay, yeah. Also, locally analytic representation theory with characteristic P coefficients is something also. Yeah.
Can you write X prism as a product, as you have on the right hand side here?
No, but you can somehow, well, at least conjecturally, you can write some kind of explicit presentation of this. If X is, say, again a smooth rigid space, you have some perfectoid Galois cover. For this, maybe let's assume that everything is. Well, affinoid, that's probably not necessary, but you can consider this space Y associated to this perfectoid cover. And this comes with an action of G, the p-adic Lie group, which is the Galois group of your poetal cover. And our guess is that in this case, you can somehow describe this prismatization as a quotient of, inside this, on this space Y for the perfectoid cover, you can in some sense work with the subshift of locally analytic vectors for this G action. And so you pass to this, you consider this space and you model by the action of GLA. So that gives you some kind of explicit presentation. But that's something which is naturally suggested by geometric sense theory. And I don't know, we always wanted to get a definition which is just a moduli definition, independent of like choosing such a presentation.
If there are no more questions, let's thank Arthur-César.